One issue with the delay-based spin locks is how to pick a good delay value. Two basic strategies make sense: static delay and a dynamic delay. For static delay, we can use some fixed information, like for instance the CPU ID, where the process is running, in order to determine a delay that will be used for any single process that ends up running on that particular CPU. The benefits of this is that it's a simple approach, and under high loads, likely the static delays will sort of nicely spread out all of the atomic references so that there's no contention. Clearly, the delay will have to be a combination of something that combines this fixed information and the length of the critical section, so that one process is delayed 1 times the critical section, another process is delayed twice the critical section, and so forth. The problem is that this will create unnecessary delay under low contention. So what if we have 2 processes? The first process is running on CPU with an ID 1. The second process is running on a CPU with an ID 32. And so they're the only 2 that are contending for the spin lock. And yet the second process that's running on the CPU with ID 32 will be delayed substantially, regardless of the fact that there is no contention for the lock. So to avoid this issue, a more popular approaches use dynamic delay. And the dynamic delay is such that each process will pick a random delay value based on the current perception of the contention in the system. The idea is if the system is operating in a mode of low contention, then it will choose dynamic delay value that's within a smaller range. So it will back off just for a little bit. It will delay just for a little bit. And if the system is opening in a mode of large contention, then this delay range will be much larger. So with the random selection, some processes will back off a little bit, they'll delay a little bit, whereas other processes will back off, they will delay for quite a bit of time. Theoretically, both of these approaches under high load will result into the same kind of behavior. So dynamic will at high load will tend to be equivalent to the static delay-based approach. The key question is, however, in this dynamic delay is, how do we know how much contention is there in the system? That's why we put here the term perceived. We don't know exactly what is the contention in the system, so each of the processes, the implementation of the spin lock, somehow has to infer whether the system is operating in low or high contention so that it can pick an appropriate delay. So a good metric to estimate the contention is to track the number of failed test and set operations. If a test and set operation fails, the more likely it is that there is a higher degree of contention. The problem with this, however, is if we're delaying after every single lock reference, then our delay will keep growing based on both whether there is indeed contention in the system or if simply the owner of the critical section is delayed or if it's executing a long critical section. So then we may end up with the same situation as before. Just because somebody was executing a long critical section while holding the spin lock, that doesn't mean that we need to bump up the delay. So we need to be able to guard against this case.